Unit 2-4 is special pairs of angles. Special pairs of angles. Complementary, supplementary. We dealt with these two on page 52 of the Algebra 1 textbook. There we learned that complementary angles are two angles whose measures have the sum of 90. Supplementary angles are two angles whose measures have the sum of 180. And then we also learned on page 52 of the algebra book that the sum of the angles of a triangle is 180. And then remember we had that little rule, Rule 4, page 52, that said to assign variables to things in a ratio, you multiply each member of the ratio by x and have only one name. Remember that? So we use that in correlation or in relationship to complementary, supplementary, and the sum of the angles of a triangle is 180. So this isn't anything new to us either. Complementary angles, abbreviated like that, comp angles, are, this is important, two, not one, not three, two angles whose measures have the sum, that means they add up to, right, of 90 degrees. Two angles whose measures have the sum of 90. Now we said not one. What do you call one angle whose measure is 90? Well, we call that a right angle. Complementary angles are two angles whose measures have the sum of 90 degrees. Those two angles may be adjacent angles. If they are, then together they will create a right angle. But they do not have to be adjacent angles. They can be two angles anywhere in space whose measures have the sum of 180 degrees of 90 degrees, excuse me. Supplementary angles are two angles whose measures have the sum of 180. Two, again, not one, are not more than two. Two angles whose measures have the sum of 180 degrees. Or we could say add up to 180 degrees. Two has to be two angles whose measures have the sum of 180 degrees. If those two angles are adjacent, then their exterior rays form a line, and we have a special name for those. They're called a linear pair. A pair of angles that make a line, or a pair of angles whose external sides form a line. Obviously, their sum is 180. You could have two non-adjacent angles that add up to 180. They're also supplementary, adjacent or not. Now, people have trouble remembering which one's the 90 and which one's the 180, and maybe this will help you a little bit. If we just go zing through the C and zing through the S, it kind of turns that C for complementary into 90 degrees and the S for supplementary to 180 degrees. Some people simply remember that C comes before S in the alphabet and 90 comes before 180. Some way or another, you need to remember that C is complementary, and that's the 91, and S is supplementary, and that's the 181. I think the cleverest trick is to make the C into a 9 and the S into an 8. I think that's kind of cool. But anyway, uh, figure out a way to not forget which one's which. Okay. And then vertical angles we talked about are angles opposite each other when two lines intersect. Angles opposite each other when two lines intersect. But that's the way we've defined them. When these two lines intersect, 1 and 2 are opposite each other. We call those vertical angles. 3 and 4 are opposite each other. We call those vertical angles. That's not really the formal definition because we have to define things according to something that we've already defined before. So here's really the formal definition. I just wanted to spare you of it. It's two angles whose sides form two pairs of opposite rays. That's actually the formal definition of vertical angles. See, these are opposite rays, and these are opposite rays, and these are vertical angles. Their exterior angles form two pairs of opposite rays. That still doesn't really help us visualize where they are, does it? So I redefined it a bit as angles opposite each other when two lines intersect, because that's really what you're going to be seeing anyway. Okay? And theorem 2-3, it's a theorem because we really could set up a two-column proof and prove it. And we discovered it before, remember, in the constructions at the end of the last homework assignment. Angle 1 and angle 2 are vertical angles. Angle 3 and angle 4 are vertical angles. This theorem tells us that vertical angles are equal, so our conclusion is that since 1 and 2 are vertical, they must be equal. And since angle 3 and 4 are vertical, then they must be equal. Vertical angles are equal. Okay? I already talked about that in a proof a while back. We discovered it, and now we're actually saying, well, here's the rule that we've been talking about so much. Okay, so three special pairs of angles. Complementary angles are two angles whose measures have the sum of 90. Supplementary angles are two angles whose measures have the sum of 180. And vertical angles are angles opposite each other when two lines intersect. And theorem 2-3 tells us that vertical angles are equal, and we'll be using that in proofs a lot in the future. Okay? So, we're going to take that information, do a little daily work. We're still giving reasons, so we're learning how to do reasons in a proof. It says angle 1 is equal to how many degrees, and what we visually see by looking at the diagram, and that angle 1 is a vertical angle to the 140 degrees. Therefore, it must be 140 degrees because of theorem 2, which says vertical angles are equal, and I allow a whole lot of abbreviating when we do reasons in a proof. So vertical angles, I have an angle with an S for angles to shorten that. A-R-E, we just put R and equal. That used to bother folks a little, but in the days of text messaging, that's probably still too many letters. So y'all are probably happy with all this abbreviated stuff these days. Anyway, angle 2 would be equal to how many degrees? Now, what you have to recall is that a straight angle is 180 degrees, right? From here all the way to here is 180. If this much is 140, then we can get the rest of it. 180 minus 140 is 40 degrees for angle 2. What could you use for a reason there? Well, you actually subtracted, but you really didn't subtract something from both sides of an equation like A equal B and C equal D. So A minus C equal B minus D. So it's not subtraction property of equality. You used a couple of things. Maybe you used the definition of a straight angle, Or you could say that these are a linear pair, so their sum is 180, and then you could subtract. But if we're going to say definition of a linear pair, we need the word and what you get out of it, you see. And so I would probably just say definition of a straight angle, because that's what I saw in the picture that told me it was 180, that allowed me to know that I could take that away. I used Plano arithmetic to go from the 180 to the 40. You may say, well, you used angle addition or angle subtraction. You took the whole big angle minus that little angle, and I did, but generally when we say angle subtraction, we actually name the angles instead of using numbers, okay? But your instructor may be satisfied with saying angle subtraction. Different teachers are satisfied with different things, but I would not be. I would want to see a big angle in letters minus a little angle in letters is equal to a little angle in letters. So the thing that told us we have 180 degrees there to subtract from is the definition of a straight angle. That's what would satisfy me, obviously. Okay? Now, a complement of something. If you want to find a complement of something, what would you do? Well, you got to go to the definition and say complementary angles are two angles whose measures have the sum of 90. So if you want the complement of something, you have to subtract that something from 90, and the result will be its complement, right? If you wanted to find something supplement, then obviously you would subtract that something from 180 degrees. Now, when we get into this next little problem, we're getting into some algebraic application. It says the supplement of an angle is 4 times as large as its complement. Find the measure of the angle, its supplement, and its complement. Now, if we let the angle be called x degrees, then to find its complement, we would take 90 minus that angle x. So we could write its complement as 90 minus it. We could write its supplement as 180 minus it. So that is a way to assign the same variable x to the angle, its complement, and its supplement. Remember, to solve an equation, we need to only have one variable or one name. Now, page 40 of my Algebra 1 textbook is how we begin to do word problems. And we said we would look for a comparison between two characters. That's page 40, step 3A. It says the supplement is 4 times the complement. Supplement is 4 times complement. Supplement is 180 minus x. Is means equal. The verb, page 37, is the equal sign. 4 times means you multiply. The complement is the 90 minus x. Page 37, we said, and page 171, page 37, rule 2, and page 171. We talked about if a higher operation like multiplication is hitting a lower operation like subtraction, you have to put that lower operation in parentheses, and if it's a one lower, we're going to distribute. Remember that from Algebra 1, page 37 and page 171. So we're going to do that distributive and have 180 minus x is equal to 4 times 90, which is 360, and then 4 times negative x is negative 4x. We have to recall the order of operations horseshoe on page 33 of the algebra text. We cannot simplify either side anymore, so we're going to be dealing with the bottom of the horseshoe. The bottom of the horseshoe on page 33 of the algebra text says, get the variable that you're isolating on one side of the equal sign, remembering to change the sign when you cross over. And so we're going to have 180 plus 3x, that's when you combine those, is equal to 360. I'm going to clear some of this other out of the way. I've already gotten into it a little, but let me white out some of the things that's right below our work there. So we've done all we can do to simplify. The variable we're isolating is now on one side, so now it's time to start undoing. So we would subtract 180 from both sides. We would get 3x is equal to 180 degrees. We're then going to undo multiplication by division, and we would get x equals 60 degrees. The question was to find the angle, its supplement, and its complement. The angle is x, so it's 60 degrees. The complement is 90 minus x, so it's 90 minus 60, which is 30 degrees. The supplement is 180 minus x, so it's 180 minus 60, which is 120 degrees. You can check to see if the supplement is 4 times the complement, and it is. 4 times 30 is 120. So we verify that that worked out. Any questions on that? Good little word problem there. Okay. There's some application of vertical angles are equal. You would set these equal 3x minus 6 equal x plus 2 and solve. There's nothing you can do to simplify either side, so our first move will be to get the variable to the other side. Okay. And we're going to leave the rest of these for you to do because you need that algebraic practice. Okay? We have a nice size proof at the end of this lesson. Let's start you on another proof, just giving reasons, just to kind of get you going there a little. I'm going to minimize that recorder just so I can show you a little bit more of that. We're still not going to be able to get it all in there, but we'll at least get you started. Remember what we said to do is to write the given proof, put the statements on the left, reasons on the right, draw the diagram. And then, even if we're just giving reasons, we're going to take what we're given, mark it in the diagram, write statements and reasons derived from the markings in the notes section. It says angle AGC. AGC, that's this angle from here to here, is equal to angle EGC. That's this angle from here to here. So we mark that. Angle AGC equal angle EGC. Reason given. And you may say, well, that's redundant to write down what's already written. But we're learning some organizational skills that's going to help us do the big, bad, ugly proofs later. And we're going to have trouble handling them if we haven't already developed these organizational skills. The next given statement says ray GB bisects angle AGC. Ray GB, that's this angle, bisects angle AGC, that's this angle. What you get out of an angle bisector is two equal angles, so from that we get these two angles equal, and we're going to put 2 marks to distinguish them separately from the 1 mark angles. I'm going to go ahead and make this red mark go all the way back across there. And so from that, we can reach the conclusion that angle 1 is equal to angle 2. And the reason is we have this word angle bisector and the what we get out of it. So the reason must be definition of an angle bisector. But we know before we can say definition of, we really need the word. And so we're going to go ahead and insert that statement that has the word in it so that we can feel better about saying definition of. So our diagram is beginning to develop. Our note section is beginning to develop. It then says that ray GD bisects angle CBE, ray GD bisects angle CGE. What we get out of an angle bisectors two equal angles, and we use three arcs to show those angles that are equal. So we reach the conclusion here that angle 3 is equal to angle 4. Reason, definition of angle bisector. We had the word angle bisector and what we get out of it, two equal angles. But there again, before we're going to say definition of, we want the word in our statements, so we know that the statement ray GD bisects angle CBE must be before the definition of. And so that was given. So we took what we were given, we marked it in the diagram, we wrote statements and reasons derived from the markings in the notes section. We don't have to do the whole proof, so we're just going to go looking for reasons. Now remember, we said you look first at the given, because if it's given, it's like, duh, there it is. Why are we looking all over the place for it? It's right there. And then we would look at the diagram, because if it's in the diagram, then we wrote it in the notes section and we've already got our reason. So why are we trying to figure it out when we've already got it figured out? The last place we would look is in the statements above it, because that's where you got to do all the how do they look alike, how do they look different, and all that. That's the last place we want to look, is the statements above. So we go to the first statement. All of this given stuff, you look up here and there it is, given, so we put given. And then it says angle AGC is equal to angle EGC, and we look up here, angle AGC is equal to angle EGC, and that was given too. Good thing we looked again. And then it says angle AGC is equal to angle 1 plus angle 2, and you look in the given and it's not there. So we go to the diagram. Now this diagram's gotten a little bit congested, I guess you can tell, but that actually said angle AGC, that's this blue one, is equal to angle 1 plus angle 2. Can you see that angle 1 plus angle 2 is equal to that whole big angle, angle AGC? Well, you can. What says that you can add two little angles to get the whole big angle? Well, angle addition says that. See, angle addition. And I went ahead and did this one because a lot of students forget about that. Well, you may say, well, why do they forget about it? Well, it's because you don't read your geometry book every day. You learn a lesson and then you forget it. A few days later, all you know is the last lesson that you learned. It's very important, especially if we're going to do proofs, that you know every definition, postulate, and theorem in the book as you go. Commit them to memory as you go. If you wait very long to begin to commit these things to memory, it's not going to be long that you're totally lost in geometry. Do not allow yourself to get in that position, okay? Let's just Well, I'm just going to let you dig on it there a little bit. We probably should let you work with that, because you need the experience, and maybe you get stuck, you call your teacher, get some help with it, go back and dig in the book a little bit. But if I do too much, I'm taking the pleasure away from you to dig it out, and the long-term knowledge you're going to get from digging